Yes. So now we will starting with the next topic, that is FET, that is called field effect transistor. So initially we have gone through with the transistor, that is BJT. Now we will be going with the another type of transistor, that is called field effect transistors. Okay. So in this class basically we will be going with the introduction part. So from next class onwards we will be going with the working of the FETs. Okay. So how these FETs are defined, we will see that, and how its construction is there. So we will go in that, like how the construction of FETs are going to be done, and the construction of FETs are somewhat different from uh, the construction of BJTs. So here the FETs, that is field effect transistor, is basically going to have three different terminals and four different terminals. Okay. So we will first start with the basics. So here in this diagram it is shown like a black box is there. This is a BJT. So here uh, based on the input current, so whatever input current was there, that is IB. So IB was the input current. So we were varying the input current. Based on that we were getting some output current. Okay. So it is basically, this is input side and this is the output side. So on input side we were varying the current, and on the output side we were getting the output in terms of current itself. Okay. So it is basically called current controlled, because input current is going to control the output current. So that's why it is called current control. So BJT is a current control device. Okay. Or we can call it current controlled current source, because output is a current. So current controlled current source. This is the BJT. But the FETs that we will be going with, that is field effect transistor. So here field effect transistors are like, it will be a black box. Here the input side we will be controlling the gate to source voltage, or this is a three terminal device it is. So this is gate, this is drain, and this is source. So this FET is a three terminal device where the input side we will be controlling the input voltage basically. So this is input voltage VGS. So whatever input voltage is there, we will be controlling the input voltage, and with respect to that we will be getting the output side, we will be getting the current. So here we are going to control the output current similar to the BJT, but this controlling will be done based on the input voltage that we are applying on the input side. Okay. So this FETs are called voltage controlled device. Okay. So based on the voltage control we will be you going to use these devices for an amplifier. So it is like a voltage controlled amplifier. Okay. So this is called, so these FETs are called voltage controlled current source. So this is voltage controlled current source. So this were, the VGTs were current controlled current source. Okay. So in both the cases we are getting the output as a current, but the controlling mechanism is different in case of BJT and in case of FETs. Okay. So we will be going with the FETs, like, so here we are going to control the output current based on the input voltage. That means if we are going to uh, change the input voltage, that means we are going to change the electric field on the input side. Okay. So whatever voltage we are applying across this, there will be potential difference, and because of that potential difference there will be an electric field intensity. Okay, so basically in case of FETs, the operation of the device will depend on the electric field intensity. Okay, that is that will intensity will that will electric field intensity that will be introduced because of the applied gate voltage and also applied uh, output voltage that we will be applying basically. So here the electric field will be developed inside the channel region. Okay, so this is like the operation of FET devices depend on the electric field intensity produced or applied, basically produced in the channel region. Okay, so there will be an electric field intensity. Based on that, there will be a current flow. Whatever electric field intensity that we have, there is electric field intensity developed across the channel, the current flow will be with respect to the field intensity that we have applied. Okay, so we can, another point we can write like this: FETs are basically like voltage control. Okay, so you can write that it is voltage, it is voltage control devices. Okay, and here in the FETs, what will be going on is like whatever the current flow will be there, that current flow will be with respect to the majority charge carriers only. Okay, but in BJTs it was like here holes and electrons both were constituting the current part, but in case of FETs only the majority carrier will be going to have the current flow. That means here we can write like here majority carrier uh, current is there, that means it is called majority carrier device. Okay, as it is having majority carrier device, we can call it like it is a monopolar device. Okay, because BJT is a bipolar device, this FETs are monopolar, that means it is having only one charge, basically either positive or negative, that means either holes or electrons that will only be constituting the current flow. So here uh, current will be because of the only one charge, one type of charge. Okay, so as there is the only majority charge carriers, there will be no minority charge carriers. So here no minority charge carrier will be there. So if there is no minority charge carrier, that means because of no minority charge carrier, there will be like the minority charge carriers are like the charge carriers that constitute the leakage also. Okay, so if there is no minority charge carrier, there will be no leakage current in case of FETs. Okay, and also as there is no minority charge carrier, these devices like the devices FETs will be having less noise. It will be having less, it is less noisy device as it is having no minority charge carriers. Okay, and also if it is having no minority charge carrier, the temperature effect will be less. We can just write like if it is uh, no minority charge carrier, so whenever we are going to increase the temperature, the minority carriers were going to get doubled for every 10-degree rise in temperature. Okay, so ICU or whatever reverse saturation current we have talked about. So minority charge carriers gets basically increase very rapidly in terms of the temperature, but here there is no minority charge carrier, so there will be less effect of temperature. Okay, so majority charge carriers vary, the change in majority charge carriers are very less, okay, compared to the minority, but here there is no minority, so there will be very less effect of temperature, less effect of temperature will be there. So if very less effect of temperature will be there, that means it will be having high thermal stability. So thermal stability in terms of FETs will be very high. Okay, and also these FETs are operated in like uh, its input side. On the input side, this FET will be operated in a reverse bias. So generally these FETs are having high input resistance. Okay, so if we talk about the input resistance, so it will be having high input resistance. So high input resistance devices are there. So high input resistance devices, so generally this input resistance will be greater than or equal to around 1 mega ohm. Okay, that means it will be uh, either 1 mega ohm or greater than 1 mega ohm. Okay, so it is showing very high input devices. In terms of BJTs, so BJTs are having low input resistance. So input resistance in BJTs, like on emitter side we have uh, find it out RE. Okay, so that was value that was ranging between around 40 to 100 ohms only. Okay, so this was the input side. The input resistance in case of common base configuration RE that we were getting is 40 to 100 ohms only. But in case of FETs, we will be getting high input resistance. Okay. Also, the power consumption in case of the FETs are very less. So here, the power consumption is very less. Okay, as compared to uh, the BJTs if you talk about, and also we will see some of the more properties compared to BJTs here. Okay, so if we are going to implement an amplifier, if we are going to have an amplifier implementation, the FETs, you can call it like the FETs are a better device for uh, constructing or for basically going to have an amplifier as an application for these devices. So FETs are better device if we are going to implement an amplifier than the BJTs. Okay, BJTs are less preferred for less preferred device for amplifier. Okay, so FETs will be preferred for implementing the amplifier as application for these devices. Okay, and also if we compare the BJT with FETs, so here FETs are of very small size compared to BJT, and also very small size, and also it is very easier to fabricate. Okay, than these BJTs. So these are the different properties of FETs compared to the BJT, and also like it is one of the important, you can say, device that is most frequently used in current uh, electronic applications. Okay, so there are some disadvantages also, like there are some advantages associated with this BJTs, sorry, in FETs. So we will just see what are the disadvantages. So in terms of disadvantages for FETs, so here the one of the first disadvantage is like it is having a smaller gain. Okay, so the gain of these devices, so gain means the output divided by the input. So whatever input is there and output is there, so gain in terms of FETs are less. Okay, and also as it is having smaller gain, it is having a smaller gain bandwidth product. Okay, that means a smaller gain bandwidth product. Okay, so this is the disadvantage associated with these FETs. Okay, so next we will go with like the construction of FETs, how these FETs are constructed, and what are the different types of FETs. Okay, so first of all we will see what are the different types of FETs. So in terms of FETs, there are different FETs are there, different types. Okay, so this is basically divided into two major part. So one of the FET is called Jfed. Okay, so this Jfed stands for junction field defect transistor. Okay, another one is called Mosfet. So here in this course, basically there are other type of FETs are also there, but we will be basically going with the Jfed and Mosfet only. Okay, so we have just considered it like it is of two types only. So Mosfet, there is another like Mosfet, Mesfet. So we will just consider only two parts. Okay, because these two topics we will be going in this course. So one is JFET, that is junction field effect transistor. Another one is Mosfet. So this Mosfet is metal oxide semiconductor. Just a minute. Okay, so sorry for the interruption. So here FETs are basically JFET and Mosfet. Okay, there are two different times we will be going with. So this JFET is junction field effect transistor, and the Mosfet is metal oxide semiconductor field effect transistor. The same. Okay, So these two we will be going in deep, like how its construction is there and how its input and output characteristics are being plotted, and that means how its working is explained basically. So we will be going with the working and the construction of these type of devices. Okay, so this FETs, so just we can have a short note of these devices just. So this FETs are of, it is a three terminal device. The three terminals of this Jfed is the source, that is S defined for source, G defined for gate, and D defined for drain. So there are three different terminals. In case of Mosfet, this Mosfet is having four terminals. It is a four terminal device. Okay, so the four different terminals are source, gate, drain. Another one other terminal is that is called body, or we call it substrate. Okay, substrate or body we call it. So it is substrate or body. It is also called bulk. Okay, so we can just call it the body or the substrate. So most frequently it is called substrate or body. Okay? So it is a three terminal device Jfed, and the MOSFET is of four terminal device. In case of the Jfed, the input resistance is of the range, like it is having the input resistance that is 10 power 6 to 10 to the power 8 ohm. In case of MOSFET, the input resistance is of the range, like it is 10 to the power 10 to 10 to the power 15 ohm resistance. Okay, and also this is having 10 to the power 10 to 10 to the power 15 ohm as the input resistance. So it is the device that is having the highest input resistance. Okay, so it is highest input resistance device. Okay, so that's why this MOSFET is most frequently used nowadays. It is having highest input device, sorry, it is having a highest input resistance. So as it is having highest input resistance, so it can be applied just before any system is being implemented. So if any system is being implemented, then as the first stage this MOSFETs will be used, because if any uh, system is having, suppose this is a system, in that whatever input we are applying, so suppose this is the input we are applying, so we need to uh, place here a device. Okay, that device should be offering the high, you can say maximum input resistance, so that whatever resistance of the circuit is there, and then suppose this device is having highest input resistance this. Okay, so whatever input we are applying, so the same input should be appearing at the input of this you can say system. Okay, so whatever input we are applying, it should not be you can say reduced, its magnitude should not be reduced in between the path. Suppose this is the series resistance associated with the input that we are applying. So suppose this is Ri is very high, then the voltage across this Ri, okay, that voltage will be the input voltage to the system. Okay, so input voltage to the system, suppose this is there, so input voltage to the system will be given by like Ri divided by Rs plus Ri multiplied by the input voltage. Okay, so if Ri is very high, then we can just approximate it like it will be Ri divided by Rs plus Ri will be again the Ri, because Ri is very large in compared to Rs. So it will be Ri. So it is this. So this Ri will be cancelled, and that means whatever input we are applying, the input voltage will be applied to the input of the system itself. Okay. So here we input to the system. Okay, the system will be getting the input exactly the same that is applied as the input. So that's why if any system is there or any device is there that is having higher input resistance, then that device should be used at the input part or the starting part of the system, so that whatever input is there, input voltage is being applied, the same input voltage is appearing at the input of the system. So this is the system. So here input voltage to the system will be the same as the input voltage we are applying. So that's why it is used as the first stage to the any system if we are going to have the highest input resistance is there. Okay. So this is uh, basic of a Jfed and Mosfet. Next, this Jfed and Mosfet is further divided. So this Jfed and the Mosfet is further divided into two different parts. Okay. So this Jfed is divided as N channel and P channel. Okay. So this Jfed is of two type, that is N channel Jfed and P channel Jfed. The Mosfet, similarly the Mosfet, this Mosfet is divided into two type, that is called depletion type Mosfet, depletion type Mosfet, and another one is called enhancement type. Okay, so it is further divided into depletion type and the enhancement type. So this N channel device, so this N channel device is there, so its symbol we can just write here, the symbol of N channel device. So this will be the symbol. So here if it is N channel, so the arrow or the current direction or this arrow will be inside. So this is the gate terminal, this is the drain terminal, and this is the source terminal. This is for the N channel device. Similarly, if it is P channel Jfed is there, so Jfed will be represented by this. So here the current will be showing like it will be outside. So if it is drain, this is gate and this is source. So this is the symbol. Okay, so this is symbol of Jfed. This is for N type, N channel and P channel. Similarly, this is depletion type MOSFET. Okay, so depletion type MOSFET is just we will see like how it is defined. So in case of depletion type MOSFET, this is having a pre-existing basically pre-existing channel. So depletion type MOSFET is the type of MOSFET where the channel is pre-exist. That means even if we are going to apply some gate voltage, before that the channel will be existing. That is, channel has been available into the device. That will be a depletion type MOSFET. In case of enhancement type MOSFET, there is no pre-existing channel. So there is no pre-existing channel is there. So that type of device will be a enhancement type MOSFET. Okay, here this depletion type MOSFET can operate in two different modes. It can operate in two modes. So that two modes will be like it can be worked as an depletion mode or a enhancement mode also. Okay, so these depletion type MOSFETs can be worked as a depletion mode, or also it can be worked as an enhancement mode. Okay, so as these depletion type MOSFET can be worked as depletion mode or enhancement mode, it is also called DE MOS. Okay, so the depletion type MOSFET, so it can work in depletion mode or also it can work in enhancement mode. That's why it is called DE MOS. That means D stands for depletion and E stands for enhancement. So it is depletion type of MOSFET is the MOSFET where both type of modes can be operated, both type of modes exist, that is depletion mode and enhancement mode. That's why it is called DE MOS. Okay, in case of enhancement type MOSFET, it can operate in only one mode. Okay, and that mode is enhancement mode. Okay, so as the enhancement type MOSFET can operate only in enhancement mode, that's why it is also called E only MOS or E only MOSFET. Okay, so this is just a overview to all the concepts in case of Jfed and Mosfet. We will next go the construction, like how these Mosfets or the Jfeds are being constructed. So our starting discussion will be with the Jfed only. Okay, so we will be starting with the construction of Jfed. Okay, so we will be just starting with the Jfed. Once we will be completing the Jfed part, then we will start with the MOSFET part. Okay, so here we will see construction of Jfed. Okay, so this is the figure showing the Jfed basically. Okay, so Jfed is a three-terminal device. We have already seen. So there will be three terminals, and that three terminals will be the gate, drain, and source. Okay, so gate, drain, and source. So here this is your drain terminal, this is gate terminal, and this is source terminal. Okay, also it is like it is constructed on a n-type device, so there will be an n-type semiconductor on which we will be diffusing two p-type regions. Okay, so one it is basically, we can write like it is constructed on an n-type semiconductor, and it has two p-type diffused regions on the n-type semiconductor. Okay, so there will be an n-type semiconductor. This is n-type semiconductor on which we will be diffusing two different p-type regions. Okay, so these are two different p-type regions are there, and these two p-type regions will be connected to each other. So these two will be connected to each other. So these two p-type regions will be connected to each other. These two p-type regions are connected to each other, and it constitute the gate terminal. So gate terminal of the Jfed is nothing but these p terminals, p regions. So these p regions, so it is these two p regions are connected to each other, and these uh, two p regions is nothing but the gate terminal of the Jfed. Okay, so the connections will be made with the ohmic contact, like there will be a metal. So this dark one will be a metal. So this will be a metal, and this will be a semiconductor. So this is your semiconductor. So metal and semiconductor contact is called ohmic contact. Okay, so there will be an ohmic contact. So that's why also in case of drain, when we are going to have a drain terminal, we will be having this as the metal, and this is a semiconductor. So metal semiconductor contact is there. That's why it is written like it is a ohmic contact. Okay, so this is how the JFET is constructed, and here the length of the JFET, like a length of the channel. So this is the channel region we call it. So it is between the region between the gate. So this is the gate. Two gates are there. Okay. So a region between the gate region is called channel. Okay. And this channel is of N type, because the substrate, or the, let's say, the basic region on which we have diffuses this uh, p-type semiconductor. So the basic structure, that is base, was of n-type. So the region these two gate terminals is of n-type. That's why it is called n-channel, because the region between these two uh, gates is called the channel region. Okay, so this is the channel region. So channel region is of n-type. That's why it is called n-channel JFET. So that's why it is called n channel n-channel JFET. Okay, so it is an n-channel JFET. So here, so here, uh, different terminals are there. So one is gate. So what is the use of this gate? So this gate terminal is the terminal that basically going to control the current flow. So whatever the current flow is there through this channel, that will be controlled by this gate terminal. So this gate terminal is basically controls the majority carriers that is moving from the, so whatever charge carriers. So this channel is of n type. So n type is having electron as the majority carriers. So electrons will be moving from source side to drain side. Okay, so whatever number of charge carriers, that is electrons or majority carriers, will be moving, that will be controlled by this gate. So gate terminal will be controlling the majority carriers moving from the source side to drain basically. Okay, so that will be controlling the uh, majority charge carrier flow. Okay, the source. So as the electrons or the majority carriers are moving from here to here, okay, in this direction. So the source is basically the region that will be providing the charge carriers. So it is called source. It is the source of majority carriers basically. Okay, so here the role of source is basically it is going to provide the majority charge carriers, or it is it is the source of majority charge carriers. Okay, and drain region. So this the role of drain region is it is going to drain the whatever charge carriers reaching to the drain terminal. Okay, so going to it is going to drain off majority charge carriers. Okay, and this is the channel region. So this is your channel region. Okay, so this channel region is basically the region channel is the region, or it is the region between these gates, or the p type regions basically. In the region between, or the space, it is the space between two gate regions. We will be writing two gate region. So the channel is the space between these two regions. So here channel length and channel width, we will be defining the term channel length. So if we just remove this, okay, so the channel length is basically uh, defined by this region. So from here to here it is called channel length, and the region between here to here is called channel width. Okay, so channel length and channel width will be defined like that. Okay, and also there is a region defined like depletion region. So always in case of Jfed, the gate terminal or gate to source terminal is basically reverse bias always. Okay, so this gate to source is always reverse biased. Okay, reverse biased. So always the gate to source terminal will be reversed biased in case of Jfed. In Jfed, this will be reverse bias. So as it is reverse bias, so this is p side and this is n side. That means it is a p-n junction diode. So there is a formation of p-n junction diode. So as there is a p-n junction diode that is reverse bias, there will be existing depletion region. Okay, so there will be depletion region because of the reverse biasing of these p-n junctions. Okay, so if and this reverse bias uh, value will be defining the depletion region. If we are going to increase this gate to source voltage, the depletion region will be going to increase. Okay, so as we are going to increase the depletion region, this channel width is going to reduce. So as the channel width is going to reduce, the current density is going to increase as the width is going to decrease. The channel width is going to decrease, the current density is going to increase. So the current will be looking like the current is going to increase in this region because the current density is going to increase because of the channel width. So this is how the gate controls the current flow between the source and drain side. Okay, so that will be defined by the depletion region, and that depletion region will be defined by the reverse bias voltage, that is gate to source voltage applied to the gate to source terminal. Okay, so this is the construction, and the working we will be seeing into the next class basically. And this is the symbol. So if we talk about the symbol, we can just have the symbol N channel and P channel. If it is N channel and P channel, this is the symbol in case of the Jfed. So we've already seen this symbols. Okay, so this is all about today's class. We will see the working of Jfeds into the next class. If you have any doubt, you can just ask. Yes, anyone? Anyone is having any doubt?
No, sir.
Okay, okay then. So in the next class we will be seeing the working of Jfeds. Okay. So thank you.
Okay, sir. Thank you, sir.